Okay, we're going to talk about section 4.6 today. So we're going to be combining in this section trig functions with some other algebraic functions. So we'll be doing sums and differences of sines and cosines. We'll also look at damped oscillation. And the purpose of this is we're going to extend our ability to model anything that's periodic, like heartbeats, sound waves, water waves, light waves, a pendulum, springs that lose energy and therefore are damped oscillation. Basically, the whole point of this lesson is I want you to get some exposure to some other functions, how we can manipulate functions to match whatever phenomenon we're trying to model, like the examples I gave here. So hopefully this isn't going to be a big section as far as there's only 2 questions in the next quiz that are from this section, and I don't know that much will make it to the test. But it is a good exercise in learning about functions, and hopefully it helps you be a little more creative in your knowledge of different functions and how we can combine them to model anything we want, basically. So here's an example of combining a cosine with x squared. This says graph this function and state whether the function appears to be periodic. So go ahead and graph it. Okay, so if you graph this function, what it looks like is this, and I've shrunk down my window a little bit with the y's to make it go a little higher here. But it definitely looks periodic. And in fact, if we think about the regular cosine, we know what that looks like. We've been studying that for the last couple days. We know that basically looks like this. So you can see that if I continue this, basically what's happening is the part that would normally be negative gets squared, and instead those negatives then go positive. So we can understand that. In fact, we know the period of a regular cosine is 2 pi from crest to crest, so we're guessing that this distance would probably be 1 pi. All right, and we can easily check that on the calculator as well. If we just do second calculate and find a maximum here at this point, it should give us about 3.14. So let's do that. Yeah, sure enough, our maximum is pi, which means that this thing has a period, and that period is pi. All right? So it looks like when we take cosine and we square it, we still get a periodic function. Just turns out the part that was negative now goes positive. All right, let's try another one. Let's combine cosine with x squared like this. So we have y equals cosine of x squared, and state where the function appears to be periodic again. Go ahead and try this one. All right, if we graph this graph and take a look at it, it definitely does not appear to have any sort of rhythmic behavior that's repeating itself. So it does not appear to be periodic. All right. Okay, let's take a look at what would happen if we added a sine to a linear function. So we have a cosine here, and we're going to add it with this linear function with a slope of a third. Now, sine, you're saying, wait, no, that's a cosine. Well, I don't think I really described this well before, but we know that sine looks like this. We know that cosine looks like this. All right? So there's no difference in these functions. Cosine and sine are exactly the same. Have the same period, have the same amplitude, as long as you have the same number in front of it here. Just is one shifted over pi over 2 or 90 degrees. That's the only difference. So basically what we know is that the sine of x is always going to be equal to the cosine of x minus pi over 2. All right, so if we shift one of them over to the right or left, 90 degrees, we do get the other one. So they're complements of each other, we could say. They're basically both sines. All right, cosine and sine are both sinusoids. Okay. All right, so let's look at this function here. If we have a cosine and we're going to subtract a linear function, and let's try to find its domain and its range. So go ahead and give that a try. All right, if you graph this function in your y equals here, it looks like this. Now this is a standard viewing window for the most part. Let me actually go to a 10 by 10. Looks something like this. Let's zoom out. Go out in the x direction here. Let's go negative 20 to 20, and it looks like this thing is pretty much a line with some kind of wave in it. It looks like it's almost a perfect combination of what you would expect from the cosine and this line here. This line is a line with a slope of negative 1/3, so it's going to go down 1 over 3, down 1 over 3. And it looks like this pretty much has a similar slope, but it's not a line anymore, it's a wave with a slope. So that's interesting. The domain looks like it would be, all real numbers. Looks like you can stick in whatever you want for x here. There's no stipulations. You can take the cosine of a negative angle. As we know from the unit circle, you can rotate this way, and you can obviously, plug in whatever negative sign you want for this into a line. So I'm going to say negative infinity to infinity for the domain. In the range, obviously, we can get out any number as well. We're going to go negative infinity to infinity for that as well. Okay. All right, let's take a look at sums of sines. So we know that sine for our standard form, we can write it like this, and we can write a second sine like this. Let's say cosine. Then when we add those two functions together, we're going to get another sine with the period of 2 pi over b. Now the stipulation that you need to pay attention to here, things that need to be the same, is that b has to be the same here. So that's what's important. This value here, b, which we know from before, controlled our period of our sines. So our period has to be the same in order for us to add two sines together to get one sine. Add two sinusoids together to get one sinusoid, and that sinusoid is going to look different. It's going to have different variations depending on all these numbers, but it's always going to have a period of 2 pi over b, absolute value of b. All right, so let's look at an example like that. I want to determine whether the following function is or is not a sine. All right, so why don't you go ahead and take a second to think. All right, so if you graph this, you'll see that it is sinusoidal. It does have a repeat to it, and it does have a period of 2 pi. Its amplitude's changed, it's been shifted, which we can't really predict how that's been shifted based on our properties that we learned about in this class, because we haven't added two different functions together like this before. But we do know the period of these is 2 pi over b, as stated above, absolute value of b, which we have 2 pi over 1 in this case. So we do know the period of this function is 2 pi, therefore it does repeat, therefore it is sinusoidal. Right? Looks like that. Okay. What about this one? Let's determine whether this function is sinusoidal or not. Take a look at that one real quick. All right. And what we learned above was that in order for a combination of two different sinusoids to be an actual sinusoid, we'd have to have the same period. And in this case, this one has a period of 2 pi over 3. This one has a period of 2 pi over 5. Therefore, these ones aren't cycling together, right? So they're gonna throw each other off basically, and that's what you see from the graph. All right. I've graphed it in a little bit different viewing window, but there's no pattern here. There's no repeat. These periods would have to be the same in order to add up to be the same. Otherwise, they're going to be like two waves, two sound frequencies, you could say. Let's say this was modeling a sound frequency, and this was modeling a sound frequency, and they're out of step with one another. They're completely different sound frequencies. There's not going to be, there's not going to be a consistent wave that that builds to some level and then goes back down to some other level, and you're not going to hear some common frequency. All right. Okay. Damped oscillation. The graph of y equals f of x cosine of bx or sine of bx oscillates between the graphs of this function, whatever it is, and the opposite of that function. When this reduces the amplitude of the wave, it is called damped oscillation. The factor f of x is called the dampening factor. All right, let's take a look at an example of one of those. All right, so if we look at this function, what we see is this graph. So just like we described above, we've got the sine of 4x, which is bounded by this function, which is, we know that 2 to the negative x really is 1/2 to the x power, right? Because we can break this up into 2 to the negative 1 times x, and think about this as really as 1 over 2 to the first power. So we know this is an exponential function, which is exponential to k, and I've graphed it here in a dotted line, or I've highlighted in purple now. So if you look at that in the calculator, I've graphed that here with the dotted line. And then I've also graphed the opposite of that, which is this function down here now, which is just reflection over the x-axis. And you can see then that it's kind of neat how this works out. But whatever function you put here is going to dampen the periodic sinusoid. So it's actually really helpful because, you know, for modeling things like, you know, a spring. I mean, a spring obviously has some periodic motion, but eventually that spring's going to lose energy and it's going to taper off. So you can model that with one of these dampened functions. All right. Okay. Let's just try some homework, and hopefully this helps clear up a few things.